Hello everybody, in this lesson we're going to be graphing tangent, cotangent, secant, and cosecant functions. We're going to start with both secant and cosecant functions. They're kind of nice follow-ons from after having graphed sine and cosine. The cosecant function is basically our 1 over sine theta or 1 over sine x function. So first off, let's start by graphing and sketching out the sine x function. Now we know that whenever sine x, or the denominator here, is 0, we're going to be getting an asymptote. So we can immediately draw in the asymptotes. These are the points where the sine x graph is 0. X is 0 here, or y is 0 here, 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 etc. So these are all the places of our asymptotes. That's why graphing the sine x graph is nice, because it leads us directly to where the asymptotes are. Okay, so now we're going to draw the min-max points of sine x, and the reason we do that is because the reciprocal of sine x is our cosecant. The reciprocal of 1 here, y is equal to 1, so the reciprocal of 1 is 1. So the cosecant and the secant graph have a common point right here. Let's look at another point. Let's consider this point right here. 1/2. This is on our sine graph. The reciprocal of that would be 2. And so we would have a point up here. And similarly, we have a point over here, 1/2, and we have the same point up here as well. We could do that with another point here. Let's call this 3/4. The reciprocal of this is 4/3, and that point might be right around there, and we would have a reflection point over here as well. So when we combine those two together, or when we graph them all together, we get something like this, where the cosecant graph has this U shape up and down. So once we've drawn the sine graph, we could quickly sketch in the graph of the cosecant. The domain would be all reals except whenever we see an asymptote, and we see an asymptote on multiples of pi. 0, pi, 2 pi, etc. Multiples of pi, n pi here, where n is an integer. Okay. The range would be all numbers that are less than or equal to -1, all numbers that are greater than equal to 1. And the period in this case is the same as a sine function. It repeats every 2 pi. Okay, so go ahead and do this. I'll give you a count of 3, and then I'll show you the answer. 1, 2, 3. Go ahead and do this one. I will show the answer in 3, 2, 1. And you notice here when I did this one, I didn't even bother to actually draw in the sine graph. What I did here is, once I figured out the period for it, I plotted out the 5 key points that I would normally use to draw the sine function. So normally I would connect these up and make a nice little sine wave, but instead I just opted not to do it in this case. I used the points as a way to draw my asymptotes here. These are where my zeros are, so I draw my asymptotes there, and then I have my min and max, which then allows me to sketch in the U shape. And so that's how I would normally do it for cosecant and secant types of graphs. Try a secant one. This is the same thing. 3, 2, 1. Let's start looking at tangent graphs now. Tangent graphs are a little bit different and interesting. So let's start by plotting out some points. Tangent of 0 is 0. Tangent of 45 degrees, tangent of pi over 4 is 1. Think about our 45, 45, 90 triangle where we have an isosceles basically. So we have opposite divided by adjacent, so that's 1. And in the case of this angle here, it's just going to be -1 because we have adjacency here, or sorry, congruency here on the two sides, but one of them is negative while the other one's positive. Okay, so let's keep on going with points. We have a point on the unit circle. We could figure out that tangent of pi over 6 is positive root 3 over 3, and we have the negative version over here. We have plus and minus root 3 for our minus 60 degrees and positive 60 degrees. And then for our positive 90 degrees and negative 90 degrees, we have something interesting going on at these two places. Now let's just work with pi over 2 first. The sine, or sorry, tangent is sine over cosine. And the cosine of pi over 2 is equal to 0. So in that case, we have the denominator going to 0. So what we say is the tangent goes to positive infinity, and technically it's undefined there. And same at negative infinity, except in the negative sense, we have negative infinity as where tangent approaches, and then we have an undefined value there as well. So we're going to draw in some asymptotes at negative pi over 2 and pi over 2, just like we have in our table. We're going to plot in some of the other points that we have listed out here. Then we're going to connect them all together. Now, this repeats. This, if we were to continue on, we would see that this graph exactly repeats itself over and over again. And our domain here in this case is, again, all real numbers except wherever the asymptotes are. And we say it's wherever there are odd multiples of pi over 2, we have an asymptote. Pi over 2, 3 pi over 2, 5 pi over 2. The range would be all real numbers from negative infinity all the way to positive infinity. And our period here is different. Our period here is only pi. Because after pi, it repeats itself again. After 180 degrees, it repeats. So our tangent graph is different in that sense. Okay, let me show an example of how we would graph out a tangent graph. This one's been transformed a little bit. We have a vertical stretch as well as a horizontal type of stretch / shrink. Now our period normally would be pi. But what we do is we divide it by the factor of b. Here is our horizontal stretch factor. 1 over pi is actually our horizontal shrink. And so we multiply that times pi. And so we get pi divided by pi is equal to 1. The period is 1 in this case. So we're going to draw in, then next step we're going to draw in the 0, 0 point, because tangent will have tangent of 0 is 0. We'll draw in the asymptotes. The asymptotes are on either side of this point. Where exactly? It's going to be at plus and minus the period that we calculated divided by 2. So in this case, the period is 1. So we just plug that in. Plus and minus 1/2 will be our period. Or, sorry, will be our asymptotes. And you can see our period here now has length 1. And this point 0, 0 is right exactly in between the two asymptotes. Okay, so we have one point plotted out, and we already know that it's going to have this kind of general shape like that. But before we actually draw that in, we're going to plot 2 more points, and those 2 other points we're going to call halfway points. And what do I mean by halfway points? The halfway point is a point halfway in between this point here and the asymptote, as well as another point halfway between this point here and the left side asymptote. So that's where the halfway point is in the x direction, right in the middle, right here and right here, but the y point is somewhere up and down here. And where that happens to be is going to be plus and minus a. So we take our stretch factor, and at the y value of plus and minus 2, we have this point, halfway point here, and a halfway point here. So we go halfway across between the two here, and then up by 2. We go halfway in between these 2 points, and then down by 2. These are the 3 points we use to graph our tangent graph, and then it gets replicated over and over again. Okay, so give this a try on this next one. 3, 2, 1. Now cotangent, let's look at cotangent. It's very, very similar to the tangent, but has an important difference. The period is the same. The way we calculate period is still pi divided by b. So in this case, b is 1, so pi divided by 1 is pi. Cotangent will have a period of pi. We're going to draw in the asymptotes. Again, this is where it's different. Instead of starting at 0 and then going on either side, we have an asymptote at 0. We have another asymptote at pi, or wherever the period is. So let's draw in those two. So this is an immediate difference between where the asymptotes are between the cotangent and the tangent. We're going to draw the intercept, x-intercept, right in the middle of the two asymptotes. So we have the two asymptotes, we go into the middle, and we draw a point right there. The halfway points are a similar idea, halfway in between these points, halfway in between these points here. We go up and down by 2, right here. So this is the point that we draw here, and note it goes in the opposite direction. So between the left halfway point, we go up by 2. The right halfway point, we go down by 2. And so we get a shape of our cotangent graph that looks like this. It's a decreasing function. Now our tangent graph, just to kind of contrast it and superimpose it on here, our parent graph for the tangent looked like this. It was always increasing, and it went right through the origin, and we had asymptotes on either side of that origin. So tangent graph was increasing, cotangent is decreasing, and that's one of the big differences that you'll see. The domain is all real numbers except wherever we have an asymptote, and that would be integer multiples of pi. The range is all real numbers from negative infinity to positive infinity, and our period is pi. Okay, so go ahead and graph these. 3, 2, 1. Remember, it's a decreasing function. That's the most common kind of mistake, to make it increasing just like a tangent. Okay, cosecant graph. We have a reflection here, so notice that reflection before you graph it out. 3, 2, 1. So here, let me just comment on this. We have the normal sine graph would look like this, but because of the negative reflection, it's actually the opposite, and so that causes the cosecant graph to kind of be flipped upside down as well. Okay, let's graph out the tangent graph. 3, 2, 1. And then we'll end on the cotangent, but look here, we have a reflection going on again. 3, 2, 1. And you'll note that because of the reflection, this becomes an increasing graph. Instead of, this decreasing function, it's increasing. This is a tangent graph, actually. We could call this a tangent graph that has been right shifted over by 1/2. So interestingly enough, we could say negative 2 cotangent pi x. We could say that's the same as 2 times tangent pi, where we shifted this over by 1/2, x minus 1/2. These would be equivalent because now this looks like an increasing function. This negative cotangent looks like an increasing function, which is our tangent function. Okay, that's our lesson for today.